Thank you, Buzidar. So today I'm going to talk about a project I started a bit back at Berkeley, and this is joint work with Arijit Panda, Shinevu, and Scott Schenker. So a bit of background before I get it started. We have been struggling over the past 10 years since SDN was first proposed in its current incarnation to address the problems and issues around the state management. For every single project we had, pretty much designing controllers, scaling controllers, fault tolerance for controllers, and the same repeat of the same issues for network function virtualization, we always had a struggle to pinpoint what it is that the system needs to do for state management, and we always came up with ad hoc de novo mechanisms to solve that specific problem. Then around last year, we had enough, and we said, okay, we have looked at this problem enough times that we now should have a good understanding of what the requirements are and what it is that we want out of a state management for network function virtualization. So with that, let me first tell you what SCN and NFV is about. I assume you all know, so sorry about the repeat. So classically, we build networks out of composition of hardware boxes, each implementing individual functions like routing, switching, firewalling, WAN optimization, and so on. And these boxes bundle control and data planes together in a single box. With SCN and NFV, it changed in the sense that functions are now in software run on a pool of shared infrastructure and with separation of control and data planes. It brought about many nice things. So flexibility and that we expect of software and getting away from the rigidity of managing an API-less set of hardware boxes. And brought about a lot of challenges with them. The one that is probably most emphasized is performance and scalability, fault tolerance, and issues around that. So what SDN and NFV's impact, obviously it had a lot of impact in the networking industry, but its impact reached far beyond. So besides the network virtualization part that pretty much everyone, the way people build network virtualization is out of the same concepts. Beyond that, the SCN and NFV, this software ecosystem offers an evolutionary path for hardware software co-design. So your features first emerge in software. You have time to think through what it is you really want. You put the features there, they mature, and once they're proven, you can take the proven pieces of feature and move it to hardware. You probably can first experiment with FPGAs. If it's really worthwhile, move it to ASIC and so on. Another thing that has happened in the past 9 years, interestingly, is that we learned a lot of lessons in SCN and NFV. And the same, these lessons and the same principles that were used in design and the arguments that were made in favor of SCN and NFV were applied to different systems to build better systems. So we have a whole bunch of software-defined projects, so software-defined X. We have storage stacks, for example, the project at Intel SPDK, which is inspired by DPDK, but for the storage stack. Key value stores people are building nowadays with, thinking of them as network functions and with the same kind of low-level principles that were inspired by SCN and NFV. So what are network functions? So network functions are pieces of network functionality built in software. Some people want to really emphasize the V in NFV. We are not one of those. So network functions, they are just pieces of network functionality wrapped in software. And there may be or may not be a separation of control and data. I assume here that there is. That there is an external controller that is orchestrating the network function. So what are the things we assume? I mean, what are the traits of these network functions? So distribution, one of the things is that distribution is the norm. So we have to meet traffic demand. For that, one box and one core is not enough often. You need to have many NF instances to meet the traffic demand. For fault tolerance, the same. To have fault tolerance, we need more than one box. Another trait is that there is NFs, SDN controllers, and so on are stateful. What are these pieces of a state? Flow tables, configuration, statistics, and things like that. And this is a very beautiful view of SCN and FE, that you can think of a state as logically centralized. Unfortunately, physically, it is all over the network, all over your instances, because there are different producers of the state, and because when the consumer and the producer of the state is different, we need to replicate the state. And final property that distinguishes network functions of today and from what we did probably in the 2000s, 90s for packet processing in software is the different expectation in terms of throughput and performance and latency requirements. So we went from tens of thousands and hundreds of thousands packets per second processing to millions of packets per second processing. We went from millisecond time scale to microsecond time scale. And this was enabled not only by the software stack becoming better, but the hardware, I mean, let's say the commodity x86 processors becoming much better in doing I/O. And that trend is going forward. The hardware is getting better, the software is getting better. What makes scaling and fault tolerance challenging in this context is a state. And you might argue the same thing is true for lots of distributed applications. There is some unique challenges here. If we didn't have any piece of the state in these network functions, scaling out and fault tolerance would be as simple as just putting up more boxes and having a load balancer that can spray traffic between these instances. But the problem is, back to the first place, is the stringent performance requirements that are put on NFV and SCN controllers, NF boxes and SCN controllers. What it calls for to meet that performance requirement, there has been many research papers that argue that a state could be local, a state could be remote. Let's build systems that make this transparent, easy for people to migrate a state to access a state remotely, and so on. But the bottom line is that to meet the same level of performance that were promised as part of the performance you expect of NFV, the state must be local, must be in DRAM, and no farther out than that. Two things. One is that why does this make sense? So the volume of a state in networks compared to the volume of packets, volume of a state changes is much, much smaller than the volume of packets you need to detour to reach this state. So it makes sense to make the state available on path for the packets rather than make detouring and forwarding packets all over the place to reach this state. Another property is that we have many, many reads, which, I mean, as expected, we have a much higher volume of reads compared to writes. And the state itself, at the end of the day, is unlike big data systems. The state itself is not that big. I think the biggest number I remember from a company, a startup back in the day, was order of gigabytes of a state when they were compiling down high-level policy rules to individual flow table entries. For a large network, the state boiled down to gigabytes of, to be in the order of gigabytes, aggregate the state in the network. It's not that we have terabytes of a state or petabytes of a state. Yeah.
So this gigabyte is how many devices?
I probably can't answer that, but it is. Yeah, it is. It was for a sizable data center, and the product was network virtualization, so nothing more flexible than that.
So most of that state is it ACLs?
So most of it, not just ACLs, but instantiating and bootstrapping virtual networks for different tenants. It was basically a multi-tenant data center, and it is basically forwarding rules for different tenants and building layering to meet, and basically dealing with encapsulation and things like that. And this number is a few years old. People might have bigger state sizes and so on. But the point holds that the state that I'm talking about is not gigantic. It is something quite manageable. For individual network functions, a recent work we had, most NFs, basically, the working set size of most NFs is in the order of kilobytes to megabytes. So the largest working set size I remember was out of Snort, which was order of 30-something megabytes with a sizable rule set.
Can you say anything about the requirements on conflicting rights? So there may be not very many rights, but if two guys write to the same thing, what are the requirements on that? And does it differ in this context than in other distributed state contexts?
So that is a big part of this talk going forward, so I will get to it. So it is mainly an argument. So what I'm trying to argue for is that unlike a general purpose data management layer, we can get away with having single writers. We can partition the state as such to have single writers. So this is a big part of the argument, and that is, I think, up to debate. But I'll get to it. It's a very good question. Pardon me. So the scalability and fault tolerance, the second point I meant to say is that bandwidth is improving day to day. Latency is not. We are adding more and more parallelism. We are getting higher and higher bandwidth links. But latency is not improving much. The software stack is improving. There are things like RDMA that cuts a lot of overhead that we now came to believe is, we now know where they come from. But at the end of the day, it is cutting that latency further down is a very, very challenging thing. And that's not the trend that we are seeing with lots of technologies today. So scalability and fault tolerance challenge is basically this, the first point entails that we have a massive scale replication. We need to have state replicated all across where it is needed. And we want to keep up with this synchronization and massive replication while keep the replicas in sync without impeding performance. So what current SCN controllers and NFV solutions often do, so I'm not saying everything and everyone, but most products do, is they take the same solutions developed for general purpose distributed applications and apply it to networks and assume that and hope that it works. What we are going with here is trying to think from first principles, what is it that we require, and build a clean slate solution. So the view that we want to provide is what probably Scott promised back in 2011 of SDN, that let's have a logically centralized view of the network and just operate on it. Let's decouple. So this clean modularity for state management, what I mean by that is making a state available where needed in the form of snapshots and developing NFs with decoupling state and compute. By decoupling state and compute, I don't mean place them at different places, but logically think of a state as something available on the box that is doing packet processing and working on a snapshot of the state and develop it as a single program and not worry about the picture on top that NFs are in different cores, different boxes, they have this much latency to each other and so on. So the view on the bottom is where we want to go to, where each and every box have this snapshot of all the state it needs to operate on.
Do we even need to think in terms of snapshot? Are you saying we should write all this as if there was a single global state that we instantaneously modified? Is that the same thing? is what you're saying?
Not quite, because the state, those views of S that I have on different boxes are different. So yes, it's actually, the reason for the word snapshot there is that if we don't put any constraint on it, let's say, oh, everything is changing all the time, it makes reasoning about applications a tad bit harder. But making the notion of everything is instantaneous, everyone has instantaneously the same view, there is no way to get around the latency that it entails. Basically, we have to update the replicas in real time in fastpath, or invalidate the cache entries in fastpath. Both of them incurs a high latency, which we conjecture is not acceptable. So where we go with this, and what we propose, is basically revisiting and rethinking distributed shared memory. So distributed shared memory has a lot of connotations attached to it. The research from back 20 years back, and lots of people told me, don't use that term. But to just give you a sense of what it is we are trying to do, I'm using that term. And probably our work is a marriage of the concept from DSM. I mean, just the notion of having shared memory. And what people do to get to basically have isolation between reads and writes, something like multi-version concurrency control in the Linux land, RCUs and things like that. So we want to put these two concepts together. So the form it takes is that we have a network fabric that connects nodes. There is a layer of shared state on top, which is our system. It has weak semantics I'll get to. To get around, to make working with this shared state easy, we want to have some building blocks that abstracts away these weak semantics and make it easy for programmers to write applications on top. What we can do is build data structures, build barriers, locks, build durable snapshot, or even consensus on top, and on top of it, build applications. So this is a set of applications we have been experimenting with in this context. Before I present you the design, I will tell you about a few of the traits and characteristics that this system has and how that is enabled. So the weak semantics I'm going to talk about, we believe, is a good match for a broad class of distributed programs. And we started from network function virtualization, but we are going and looking at a broader class of applications. And we are trying to work around what you might think of as deficiencies of and drawbacks of traditional and canonical DSMs. So first, all threads, whatever state they might require, they can read it locally. But update visibility is delayed. So reads are fast, updates might be delayed. How we do it is by versioning memory regions. So a piece of address space you have, it might be different. You might have a different view on different threads. It might be different versions. And obviously, the reads might be stale. So we are putting availability above all in the system. But our target is to update these snapshots at the millisecond time scale with a very low overhead. Synchronization in the system is eager, it is fast, and it incurs a very minimal overhead in the fast path. How we do it is we do bulk data-oriented synchronization in fast path instead of process-oriented synchronization. What we mean by that, instead of copying commands, replicating commands or function calls or messages, we are replicating the result of computation. And synchronization, basically, there is some network I/O to it. There are expensive parts to it, packetization, network I/O, and those parts. We split up synchronization in two parts, what we call into internal and external synchronization, to offload the slow part of synchronization to the slow path. What this entails is that the apps now have to organize their state into single writer memory regions. This is a big constraint, but we believe this is something we can work around in this context. So this enables conflict-free data-oriented synchronization. What is wrong with data-oriented synchronization is that if a conflict occurs, you have no way of resolving it because the semantics of the application is lost. How to work around having single writers, there are many techniques. You can have delegation, you can use the state-based CRDTs and combine. You could use flat combining, or if you really need to, you can implement multi-writer on top. So what it entails is that you have to have the knowledge of how the logging and the snapshotting works in the system and work around its constraint to implement multi-writers on top.
Who guarantees the single writer property? Is that something that the programmers are required to guarantee, and if they get it wrong, then things just go wrong?
So
In
terms of, it is very easy to do it by just at the page level marking pages as read-only. We don't do it in our current implementation. So the reader threads, when they're mapping an address space, we can always tag it as this is a read-only space. And there are new CPU features to make it easy to do this from user space at runtime, not as a security property, but as a debugging mechanism that if there is such a violation, it will be caught. But in our current implementation, we are not doing that. We are assuming the application developer is aware of the single writer, that they are the owner, and they will be the only one writing to the...
If two do write to it, then just bad things, unspecified bad things will happen.
No, I mean, not necessarily, because the read-only region is only visible to the threads on that machine. That update will not propagate throughout the network. I mean, it's just because how we don't really collect updates from read-only regions. That is a side effect of implementation. No, bad things may or may not happen. So the basic building block is a notion of areas. It's a unit of memory allocation. So when you allocate a new area, you get a continuous byte stream at a fixed address. So if the address is X on machine on thread 1, it will be the same thing on every thread that will map it. So you can use your naive old data structures and lay it on top, and it would work. So these areas are versioned, time-stamped, and versioning entails that we must be updating atomically. So we guarantee that they're atomically updated. And the thread is able to find a staleness bound that, okay, this area is stale by at most 10 milliseconds. It does not give the application, directly does not give the application the ability to know if it is the last write, if this is the last state. That is a limitation. So areas are organized in a hierarchy. So each area has a parent. Even though we have a flat address space, we just define each area that we allocate has a parent. And that parent, the reason for that is for fault tolerance. It's just putting some thread in charge of failure detection for specific areas. Has it?
The parent is a thread, not another area. So it's not a hierarchical arrangement of areas.
It is
its own areas, is that right?
It is for hierarchy is within areas, not threads. But the thread that is the owner of the parent is in charge of at the moment. Whoever is your parent's owner is in charge of detecting if you died.
Okay.
Does it make sense? So if it happens that the parent dies and somebody else takes over and becomes the new owner, that thread is in charge of failure detection.
Each area has a parent that is another area.
Yes.
And each area has an owner that is a thread.
Yes.
Okay.
That is true.
Okay, that's very helpful. And just you said atomically updated. So somehow, how are the
It's not the world.
How are the boundaries of the transactions?
So it's explicit. So synchronization, which I'll get to, is explicit. So in the fact, it's very much like RCU or any other similar mechanism that you say that I'm out of the critical section. I'm out of a read region or write region. And all the threads frequently call into, whenever they are in a safe state, they call into a service function that signals that it's now time, I can enter a synchronization phase if you need me to. I'll get to it in a bit. So explicit membership is another notion. So in this picture, we have area 0 owned by process A. Process B and C are attached to it. They are in different versions. You can see that on machine A, process for area 2, only process B is attached. Process A is not subscribed to that area. What this mechanism provides us with is scoping. So we don't get all the updates for all the areas that exist in the address space. So you can partition and limit the update traffic. So the building blocks at a very high level, because I'll get to it in a second, I will just briefly mention it. So software, what we are doing to track writes is software write tracking, something very simple, with user-defined granularities. So at compile time, you define what the granularity of write tracking you want it to be. So what we experiment with is 64-byte granularity, because it's what the architecture we're working on is very well tuned for. So every time there's a write to an address, we expect the application to say log write, I wrote to this address these many bytes. The application can choose to do one log write for many following writes, or it can choose to displace that log write to basically make the write visible at a later time, and all the flexibilities are with the application. The reason we are not using hardware mechanisms is the granularity. We don't want, so hardware right now provides PML, page modification logging, but it's at a page granularity. We want to go at the granularity that the user wants and needs, and as we show, the overhead is really low for this. So there is no reason to go with hardware.
But again, if you fail to advertise the write that you have thought, unspecified bad things can happen.
No. So it's your intention that, if it is your intention not to make the write visible, imagine we have some machine learning use cases like this, that there is no reason for me to make this write immediately visible. It might be overwritten as we go on. So I will choose to only make it visible at the end of, 1 second later. So I only call log write then. But the burden is on me. There's a way for the application developer to optimize and things like that. But that's a good question. This is invoked by applications, and in a specific case by the daemon. Synchronization, now the main part is scheduled by a daemon. So we have a daemon running on each machine. This is per user-defined interval. So there's an internal synchronization and an external synchronization. And the user defines do internal synchronization in 5 milliseconds, external one every 20 milliseconds. The internal one, what happens is really simple. We have, for each area, we have 2 copies. The internal synchronization is walking the log. So having all threads cooperatively walk all the logs for all the areas that are subscribed to in the system, and cooperatively copy changes from the writer copy to the reader copy. So during this phase, we are stopping the word, not doing any processing. So it's very important to make that fast. The external one is the part that we are pushing updates from the read-only, from our machine's read-only view external to the network, to push it, packetize the updates, and send it over the network to everyone else subscribed. Area management means we have allocation, deletion, ownership management, and things like that. There are some set of management features mainly implemented by a daemon, and that is discovery, to help with discovery, help with bootstrapping, help with failure detection and recovery. The last one is by daemon, mainly. And this is a DSM system, but at the end of the day, for timely notification, you can think that it should be obvious by now that there is a lot of delay between things. So if you are bootstrapping a system and you are depending on lots of teeny tiny operations at initialization time, it may take a long time. There is an RPC that we build a lightweight RPC mechanism to enable us to implement the doorbell mechanism or lightweight notification. At a high level, this is just to go over what happens in runtime and what the system looks like. So what we assume is that the process, the daemon first comes up, initializes Tasvir. A daemon on the other machine comes up, initializes, and joins whoever the root of all these areas are. And the threads come up, initializes, each thread calls initialize. And there is a new area allocation. This area gets allocated on machine A. Similarly, on machine B, we are going to attach to this area to start receiving the updates. So machine A, during the normal course of operation, whenever there's a write to the area, it will call log write, phase 1. And it will continuously call a service whenever we are in a safe state, out of critical section. The daemon is going to schedule and basically flip a bit for a thread that now enter a barrier for bulk synchronization. And when it is time, we'll enter phase 2, during which all the threads will cooperatively walk that log, change the copies from here to here. And after this, we move on. The applications will move on, but the daemon in the background, when it's time for the external synchronization, will go over the log internally maintained in the area, copy all the changes, basically packetize all the changes, and send it out over the network.
Within a machine, you can have multiple threads right into the same area.
So by default, no, that's what we assume. There's only a single thread. So single thread is, threads can attach to the writer view or the reader view. The default assumption and the default is that only the owner attaches to the writer view and everyone is attached to the reader view.
And then both the threads would walk their logs and then transfer this to the read copy. Did you mean?
Oh, they all can see the log. They can all see the reader and writer copy. There is no, I mean.
When you say they do it cooperatively, what does that mean?
So each thread in the system has both of these areas mapped in its address space. Depending on if you are a writer or a reader, you basically swap the mapping so that the area.
Who applies the log to the read copy?
So every single thread that enters bulk synchronization, we chunk up the log, the daemon chunks up the log, and each thread walks a part of the log and finds if there is anything changed from here and copies it over from here, regardless of whether it's a reader or a writer. So during that bulk synchronization phase, every thread is going to read from the writer copy and copy it to the reader copy.
Dependencies on the log, you have some kind of version to decide not to apply a copy that has been overwritten by another thread.
So we have very specific alignments that make sure that, so we give, let's say, 2 kilobyte chunks of log to each thread, and just giving that region of the log ensures that these threads will not overstep each other at any point in time. So we are basically giving different, yes, they are partitioned by the address range they are traversing. But this is a work stealing mechanism. We can talk about it afterwards. There are lots of details here. So upon external synchronization, when the data is received on the remote machine, it acts as if it's the writer on the scratch area, will log the writes for the received packets, and a similar internal synchronization will make the data available on the remote machine. So is there any questions about that? It's a bit of a rush.
Would it be right to say that the internal synchronization kind of establishes a consistent snapshot that the daemon sees, and the external synchronization is like the daemons all talking to each other to make sure they got to swap snapshots?
Yes.
Is that roughly right?
Well,
yes.
Is it consistent across regions?
Well, yeah.
Across areas, sorry.
So for a single, for the threads owned by this, owned on the same machine, yes. Not for the threads on different machines.
So you actually wait for everyone to be out of critical section.
Yes. That is, so here, the runtime is that of the slowest thread. So if somebody is taking longer to copy all the changes, everybody has to wait for it to be safe to exit. So it is consistent. So pardon me, it's always consistent in the sense that there is no turn rights ever in the system. How we ensure it is that we are stopping the world. There is no way in time that we are doing a read and write to the same area at the same time in an unsafe manner. But we are stopping the world for that. And the way to make it fast is with cooperation, with data-oriented synchronization, and so on. So you.
Just following up on Miguel's question. So if I'm a reader and I read multiple regions, I only really see a consistent snapshot if all the writers for those regions were on the same machine.
No. You see a consistent snapshot of all the state in the system. It might be, you see the latest version of the thread, almost the latest version for the areas hosted on the same machine. But for the areas that are farther away from you, the owner is farther away, you'll see a more stale version. So each area with the same version number across the network, the content would be the same. But areas with different version numbers, they are self-consistent. There is no consistency violation within an area.
What about readers who want to read different areas?
Yes.
Do they see a consistent snapshot across them, across the network?
What we define as consistent is, what we define this as is that this is consistent as long as there is no turn right for individual areas. But it might be that they are not necessarily seeing the same snapshot. They are seeing a consistent snapshot. The version numbers that the VS in the picture I showed earlier might be different depending on where you are. If you are, let's say, in China seeing an update, this is just an extreme example, seeing an update in the US, the view of this, the snapshot of the state you see in the US is very different than that of China, just because of the latency you have. And if there are some areas that are updated in China, some areas updated in the US, for half of them, you have a more recent view than another half. I hope.
I think what you're saying is that you don't have a mechanism to have a transaction across areas, right?
No. This is much weaker semantics than providing transactions for things that are not hosted on the same machine.
Some notion of transaction, if you want, within an area.
Within an area, and so one thing you can think of is that if you can reclaim ownership of an area, so you have two areas, you are the owner of both of them, you can safely write to them and make sure that the writes happen everywhere at the same time. But in the general case that the writers are at different place, the system doesn't do anything about it. You can build much slower mechanisms on top to provide transactions, but or stronger forms of multi-version concurrency control, but that's not what the system does. You're absolutely right about that. So, question that should be popping on in everybody's head is what is the overhead? It looks like it should have quite a bit of overhead. So there are three main overheads, ignoring the elephant in the room, which is we are doubling the memory requirements for the application. So because we are maintaining 2 copies of each area in the system. So if the original state was 3 megabytes, now it's 6 megabytes because the readers and writers are looking at different areas. The first part of the overhead is logging. So in software write tracking, which is a step 1. Internal synchronization, which is basically walking the log and copying all the changes. And finally, the indirect overhead, which is this process will have some, will induce some LLC contention, will have its own footprint, memory footprint. So summing up logging and internal synchronization is not enough. If it reduces, it's not enough to say that we have a very low synchronization overhead.
Synchronization too, which costs.
So that shows up in indirect, but it doesn't directly show up for applications because a daemon, a background daemon, is done in asynchronously and in background. Yes, it is. It shows up here. You're right. So when we are, for every change, we are making 3 copies essentially. We have it in the reader, we have it in the writer, and we have a buffer structure to packetize and send it over the network. So essentially, at the end of the day, we might have at most 3 copies. So what we see in practice is this, is that logging is quite lightweight. This is true for realistic workloads. You can, so logging takes 20 cycles, roughly 20, 30 cycles, plus reading a cache line, very likely, if it's not in the, it's not cached for the log. So roughly around 1% of runtime overhead. This is compared to a single-threaded application with no with no synchronization whatsoever. The internal synchronization part, we are walking the log. The log that I talked about is not hierarchical; it's just flat. For if it calls, the application calls for it, we can make it hierarchical. So log the logs as well. But as is with 64-byte granularity, with no changes, just walking the log, it takes 1 microsecond to cover 1 megabyte of address space. So if you have 1 gigabyte of address space, it takes 1 millisecond. But if there are modifications, depending on whether it's in fastpath or not, it takes between 100 microseconds to 1 millisecond per megabyte per core. So both numbers were per core. And the nice thing about it is that because it's cooperative, it scales nicely for most cases. And it scales near linearly with the number of cores. So if you have one writer aggressively writing and updating, but you have 24 threads on the machine, 24 cores, they will all cooperate to copy all the changes. Your throughput from 1 to 10 gigabytes per second can jump to, let's say, 20 gigabytes per second to 50 gigabytes, 60 gigabytes per second, depending on how many threads are cooperating to make that internal sync work.
In my extremely limited experience, it's not so much the time for the internal sync, but the time for everybody across the whole data set to get ready to do internal sync. Yes, the sort of barrier bit. Yes. That can dominate this part.
So for the application, that is a big constraint on the kind of application we support, in that they have the critical section should be really small, and they should be frequently calling into the barrier bit. So what really happens in our design, we have a grace period. That's to say, wait for 10 microseconds. It's a compile time constant. Wait for 10 microseconds. If you didn't succeed in entering the barrier, just let go. You try again in 10 microseconds. So in our experience with most of the applications we tried with packet processing, even with large number of threads, they can enter the barrier successfully.
Across the entire data center.
No. This is on a single machine.
Oh, I thought
no.
Internal.
Oh, it's on a single machine.
Synchronization. They all had to do it at once.
No. It's on a single machine.
Oh, that's
on a single machine. Sorry. That would have been horrible.
I was worried.
Yes. Yeah, that's on a single machine, just synchronizing all the cores to enter a barrier together. Because essentially if somebody else is reading a copy on a remote machine, there is no way it will conflict with this copy. So this and this have nothing to do with one another. That's a good point that I should have been clear. So the line in between in machine boundaries. Internal synchronization is really internal. External synchronization is what goes across machines. Oops. So indirect overhead for realistic workloads, we observe to be around 10%. So all these numbers could be much higher if we go with a very aggressive adversarial workload, which is the next slide. So for this, we allocate a single area with a single core. This is just numbers for a single core. And see, for different area sizes, for different synchronization intervals, what is the overhead for different parts of the system. So the logging overhead, the synchronization overhead, and the indirect overhead. So you can see, as you expect, this is the work, the micro benchmark is updating a random location in memory with some stride, so a stride of 8 bytes, I believe, for this graph, updating the region. And it's a write, it's back-to-back writes, 100% write. So this is exercising, just stressing the system quite a bit. So if we do, what it entails is that, let's say in 1 millisecond, that workload for a 16 megabyte data set can pretty much rewrite the whole region. So if we are synchronizing every 1 millisecond, over 1 second, we are doing 1,000 times, roughly 1,000 times, and we are copying 16 gigabytes of data per second. This is the number in the middle, and this is the synchronization bit. Why the indirect overhead is so large for that is because that's exactly where things, the borderline where things fit nicely in the cache alone. But as soon as we start adding a second copy and all our overheads, we are starting to make things bad. So the trend for this micro benchmark, you observe that synchronization overhead remains pretty much the same between 16 megabytes, 64 megabytes, and 256 megabytes and going on. The reason for that is rather straightforward. The amount of data that one core can change in 1 millisecond, no matter how big the data is not getting bigger. So you pretty much can update 10 megabytes per millisecond, some number along those lines. And as you go with larger areas, the chances of you updating more is less. So these numbers are specific to Haswell. On Broadwell, they look different. On Haswell and Broadwell, they look pretty much the same. On a Skylake, because of the changes in the cache hierarchy and things like that, they'll look a bit different. But we can talk about it offline if anybody is interested. So just a quick overview before I get to the applications bit. So the semantics of this layer is that we have areas that are versioned, atomically updated. The reads are local and possibly stale. The logging is in software with tunable granularity. And the synchronization has user-defined intervals. Internal one as bulk by all threads. External one as asynchronous by daemon. And the application interface is simply area management, logging, writes, and explicit bulk synchronization. So the common design patterns that will follow and we commonly use, there are a couple of very simple ones. One is combine aggregate multiple areas into one. So we have multiple publication lists, you might think of it. And one thread, who is the combiner, will combine them into one republished area. This is just to mimic a multi-writer scenario, but in a different way.
Wait, you're saying this is a way that a client of this API can build an abstraction on top that does something more powerful. So you don't have to change your underlying system at all. This is just a library, an example of a library you can build on top. Is that right?
Yes, exactly. So the last, we have two examples building on this. One is a telemetry application that you collect the statistics from all across the data center, but for you to do it in a flat way, it's very expensive. There's lots of traffic if you do it at a fine granularity. What you can do is to summarize the areas that are published by each machine and aggregate on one of the machines, republish the summary to others. So not everyone needs to subscribe to every node in the data center. People can subscribe. I mean, at the rack level, you can subscribe to the summary of that rack and things like that. So it's just, you can overlay the way you think your data should be structured and represented nicely with this application. Another example is machine learning one, but I hope I get to it. There is not much time left, but let's see. The second one is scope membership, which I alluded to. So if everybody subscribes to every area, you can easily see that with lots of writes you cannot sustain. There is not enough bandwidth to move that many bits around, and you may not want to do it even. So scope membership enables to do it. Pre-partitioning is state and ownership transfer. Lots of works in NFESC and talk about dynamically repartitioning the state, transfer of, delegation and things like that. It's rather complicated. What we can do here and what we have done with, let's say, an elastic load balancer is we essentially have a hash table. We want to have a DHT, but in memory, basically, a front-end hash table that says which of these sub-hash tables will contain the flow entry, but hosts all of them in memory in one machine. And as soon as we need more to scale reads, imagine writes is not the problem, reads are the problem, we can boot up a new instance and subscribe to those areas. If writes is a bottleneck, writing is a bottleneck, we can transfer ownership to these individual hash tables to a new one rather than repartitioning the state. If it makes sense, it was rather quick. I'll get back to this in a bit as well. Failure detection and ownership transfer. So one thing I didn't mention is how this works when a thread fails. So if a thread fails, the parent is supposed to find out, to detect it. with timeout and things like that, and just find another thread with the most recent view and delegate ownership to that thread. So now we know exactly who is in charge of failure detection. The only exception to this is all the way up to the root. If the root fails, we don't have any parent to decide who takes over, so there is a consensus round that needs to go on there to decide a new root.
Not lose updates.
Yes, I can.
When you're going to lose updates, you said that you pick the thread with the latest view.
Yes.
Become the owner, right? So you might lose.
Oh yes.
Some updates, right?
Yes.
Sure
That is.
bound on that, right?
That is a big, yes, that is a trade-off we make, that we want to keep a state in DRAM, don't make durability part of our system. One thing I like about Farm says that, oh, let's keep the state in DRAM and use battery-backed system to just persist it when needed, when things fail. So
Recovering from battery-backed here, it would probably not be a good option for you, right?
why not?
Availability might not be good enough.
Oh, yes. So yes, that is totally true. That is a true statement. So what goes on is that during the failure phase, reads are fine. It's just writes that are affected. You cannot update the area. So it depends on you pick your poison. Either you're fine waiting to see all the updates from wherever you're persisting them, or you're fine losing a bit of a state from the last version that is visible across the network and go from there. I would personally pick to just lose some state, a few milliseconds worth of a state.
When you say timeout, you have some sort of heartbeats going between machines, is that the idea?
Yes.
And they follow the same hierarchy as this parent.
Yeah, so we bootstrap the Tasvir areas for node management, thread management with Tasvir itself. So threads update the heartbeat in the area and it will become visible. So everybody is able to see when was the last time a thread checked it. But it's bootstrapped with the system itself. So in the interest of time, I will go over this very quickly. So one thing, OpenFlow came out of Stanford, Berkeley as a joint work. We didn't like it from the beginning. I mean, something is wrong with this. And it abstracts data path as match action flow tables. And there is a very detailed protocol defining how to essentially manipulate a remote flow table to match what you intended. Usually controller is the updater in the SDN case. So there are three approaches to make this work. Is process OpenFlow messages in line in the data path. Some switches do this, that you receive an OpenFlow message, on the same thread you update the flow table per the message. One option which some other vSwitches take is that there's an agent, there's a controller agent that has a shared lock over the table, or has, by some RCU mechanism, will update the table for you. So that it's not the data path that is processing those messages, but an agent on the data path. So it essentially involves some sort of synchronization and locking. And the last part is, let's forget about all these protocols, wire formats, everything, and just make it a pure byte copying, that we are constructing the data path in the same byte format. In the controller, we are just copying the change bytes with Tasvir. So what we see is this, is that if we use, let's just look at fine-grained locking in a Kaku hash table and compare it with no locking by using Tasvir. So the throughput, the read throughput, this is for an update-heavy workload. The read throughput is minimally affected with Tasvir, even at the fine-grained synchronization intervals. So basically, the loss of throughput is due to the synchronization overhead, whereas with locking, we lose a lot. Another thing this enables, imagine you are really into a new mechanism that is, the updates take a long time, but the reads are really fast. The data structure you're really fond of, you cannot deploy it because it will stall the fastpath. Tasvir is a very good thing for you to resolve that issue, because it will offload the writes to another thread and make byte copying the main issue. So what we are trading is update visibility to get a better scalable system and isolate reads and writes. Another thing is that the visibility latency is bounded. So high-level point for this graph, I will just tell you that takeaway point is that this system gives you knobs. you decide whether you want to trade how much synchronization overhead you're willing to incur and trade it with visibility latency. So yeah, got it. Another example we have is elastic fault-tolerant load balancer. It builds on the same concepts I talked about. So we have an in-memory DHT in the beginning of time. All the areas is owned by one instance. On demand, we add more instances and we partition writes. The end of the day, we want to see how scalable it is. So within one machine, it scales quite linearly. Across machines, it scales near linearly as well. So we essentially are able to have a stateful load balancer, which is what everybody is trying to avoid because it's hard to make work, but make it linearly scalable. And what I talked about, it applies more broadly to networks. So these two examples I mentioned, so CP, control plane to control plane interactions, control plane to data plane interactions, building distributed data planes, and finally building telemetry, network-wide telemetry. The same as abstraction could replace a lot of different protocols if you are fine with going with a data-oriented approach. One last thing, we tried it on different examples. Mini-batch stochastic gradient descent was something ML people at Berkeley said, why don't you try this and see if it helps? So we were trying to mimic a parameter server where Tasvir is taking over. So this is the aggregation pattern that we have workers working on local updates, aggregated on a local area, aggregated on at the global step. So for a head-to-head comparison, we compare with a shared memory implementation, native shared memory implementation, which has no contending writes, which is cyclates at NIP 17, if I'm not mistaken. And we match the native shared memory overhead, and we surpass it when there is after some thread, with more than some number of cores. And I will pass this. And so finally, okay, the premise of the work is that copying data is faster than replaying compute for a broad class of applications in networking, and we are looking at applications beyond. This
even that doesn't rely on if you've got a lot of data and a small deltas, copying the deltas is easy. If you've got little data and a lot of deltas, then copying the data is better. Doesn't it all depend?
Yes. So the class of our conjecture is that the class of applications we are targeting has the property that the state is small, the deltas is small compared to the volume of packets we need to displace in comparison. So it makes sense to replicate the data, and with that, it is much cheaper to replicate state and data rather than replay the messages that generated that data, replay the compute that resulted in that data. But it all depends. If you have a workload that has a function called mapset 2 gigabytes of data to 0, and I don't have any compression in my system, it would be a horrible system for that. So it all depends. This is not a general solution. It's for a niche class of applications. So one other thing that is nice is that this is a hardware-friendly mechanism. The mechanisms I talked about could be a specialist for different architectures. So if you have wider instructions, vector instructions, you can do faster copies. If you can relax memory ordering constraints in x86, you can use it. If you have RDMA, you can the networking and packetization bit can be made much cheaper. Hardware lock tracking, if it ever becomes available at a fine granularity, you can use it. This data-oriented nature, at the end of the day, lends itself very well to CPUs and offload. What rapid snapshotting is, which is essentially the crux of the work, is that we are doing snapshotting at millisecond time scale, enables us to move functions off a fast path. Imagine somebody asks for durability. 3D crosspoint is Intel starts selling 3D crosspoint DIMMs, and you want to make the data persist, and you have a fault-tolerant solutions. Customers don't want to go and build a new solution out of it. What they could do with this system, boot up an instance with 3D crosspoint attached to it, and start persisting a state to that off of fast path on a thread that is not serving traffic. And then we are interested in investigating other applications, and we are open and evolving the design as we go. This is an ongoing work, and I'm very excited to learn what you think, and in our one-on-ones talk about it. Thank you so much for listening.
Everybody had loads of questions. If you have any further pressing questions, otherwise I guess we can also meet afterwards. Okay, thanks again.
Thank you.